Hey folks, it's R&D Diesel and welcome to part 2 on how a 7.3 Powerstroke works. And this time we're talking about the high pressure oil system. Last time, in part 1, we talked a little bit about the overview and a history of the 7.3 Powerstroke. We also explained why we might need a HEUI injection system. We talked about how mechanical injection pumps are very limited in terms of their capability. They simply cannot account for air density changes, and that's something that we needed to take advantage of using modern computers. Now before we get too far along, we need to break down what the HEUI injection system really is. Now we can start off by defining HEUI. Now HEUI, simply put, stands for Hydraulic Electronic Unit Injection. However, if we break this down a little bit further, we get a little bit more of an understanding as to how the injection system works. Hydraulic indicates that this injection system relies on hydraulic principles of pressurizing oil to very high pressures, and then using that in essentially a hydraulic cylinder, if you will, much like agricultural equipment uses, and a lot of your heavy-duty road equipment does as well. Electronic simply means that this injection system uses electronics. In other words, it has electronic control, uses computers. Unit means that we are using a unit injector. In other words, the whole system is combined in the injector. And really the injector is where the heart of the HEUI system is. But we'll cover that in more detail in another video. And of course, injection is, as it implies, covers the injection system, how you deliver fuel at the necessary high pressure at the right time in order for combustion to occur at peak efficiency inside the diesel engine. Now in general, the HEUI fuel injection system consists of a high pressure oil pump, which supplies oil at high pressure to oil rails that in turn goes to feed injectors. Now you can think about this high pressure oil as essentially being the energy that the injectors use in order to fire. The oil is what really does the hard work and supplies the amount of force that is necessary to generate the extreme pressures that are needed for injection of the diesel fuel. So now that we know what the high pressure oil system does, it's now time to figure out how it actually works. At the heart of the high pressure oil system is, of course, the high pressure oil pump. Now this should not be confused with the low pressure or engine oil pump, as that's what's already in the sump of the engine that supplies the oil for all the bearings and the valve train as well. However, the high pressure oil pump does use the low pressure oil pump as a source for oil. If we were to trace the engine oil through the system, oil is first picked up by the low pressure oil pump inside the oil sump. Of course, this is located inside your oil pan. Now the low pressure engine oil pump, which already pressurizes oil to your bearings and whatnot, it also supplies oil for a high pressure oil pump reservoir. Now from that reservoir, the high pressure oil pump then takes the oil. After the fact, the high pressure oil pump does its magic and sends out the high pressure oil to the oil rails where it's used by the injectors. Now to say that a high pressure oil pump does magic is actually a little bit of an overstatement, when in fact all it really does is science. When you get down to it, the high pressure oil pump is really just that, a pump. And with that, we can define and understand how it works. Inside the high pressure oil pump, there is actually a large metal housing that is essentially a series of cylinders that contain pistons and springs. And this is basically the heart of the high pressure oil pump. And that's because the high pressure oil pump is what's called a swash plate pump. But to get a better understanding of what this means, let's start by building the simplest pump we can using nothing more than a piston and cylinder.
If we think about it, the simplest of pumps that we can build really just consists of a piston and a cylinder device. Now the way this pump would operate is that we effectively have the piston moving up and down inside of our cylinder. We also have a series of check valves that only let the fluid in on the inlet port and out on the exit port. At the start of the stroke, the piston moves down and it effectively brings in a series of fluid into the piston cylinder device. Then, once the bottom dead center of the piston is reached, it starts to make its way back up and it effectively starts pushing out the fluid through the outlet port. And of course, these check valves will ensure that the fluid doesn't go back through the inlet. It only escapes through the outlet. Now, what we've effectively created here is what's referred to as a positive displacement pump. And that's because it positively displaces a certain volume of fluid for every piston stroke. So now that we have the basic geometry for the pump, we've got to determine how we're going to drive this pump. Now if this is your engine, for example, the most typical way that you drive the piston cylinder is by way of a crankshaft. And of course all the crankshaft is simply a regular shaft that has an offset on it that as it rotates, it effectively pushes the piston up and down, which effectively gives it the stroke. Now, while this is perhaps the simplest of means with which you can drive the pump, it's by no means the only way that you can drive the pump. Now, since our piston only really needs to move up and down for the pump to operate, that means that any means that we can get for the piston to move up and down will technically work. Now, another way that we can get this piston to move up and down in our pump is by way of this device called a swash plate. Essentially, all it is a rotating disc that is kind of offset in a certain way such that it doesn't spin exactly flat. Now, the following animation should kind of make this point a little bit clearer so that you can see how it works. As you can see, as the disc rotates, the pistons around the disc move up and down with respect to one another. This effectively creates the same motion that a crankshaft would have, but effectively we can arrange the pistons in a circular fashion rather than an all-in-line fashion. This makes the pump a little more compact and allows for varying geometry. Now, bear in mind that the motion of the swash plate relative to the pistons is just relative. What that means is that instead of the swash plate moving, we can actually have the piston and cylinders themselves move and keep the swash plate stationary. Now, this is exactly how the 7.3 Powerstroke's high-pressure oil pump works. Effectively, the piston cylinders are rotated around a stationary swash plate, which allows them to get the up and down pumping motion. Now, another term you may have heard of refers to the swash plate angle of the high-pressure oil pump. Now, early model 7.3 Powerstrokes came equipped with a 15-degree high-pressure oil pump. Later model Super Duties came with a 17-degree high-pressure oil pump. Now, that angle simply refers to the angle that the swash plate is mounted at. By adjusting the angle that we have, we can effectively increase or decrease the piston stroke to increase or decrease the amount of oil that is pumped per every revolution that the pump rotates. By increasing the swash plate angle, we can effectively increase the pump's output. Now, later model Super Duty 7.3s equipped with 17-degree H-pops had a higher oil demand due to their injector design, but of course we'll get to more on that later. Up till now, we've established that the high-pressure oil pump is of a swash plate design. We know that it takes oil from the high-pressure oil pump reservoir. Now, the oil is, of course, supplied from the low-pressure oil pump from the oil pan, but this ultimately goes to the high-pressure oil pump and is sent out to the oil rails. Now, while there are a few odds and ends, such as springs, check balls, non-serviceable ports, and whatnot, the basic idea of how the high-pressure oil pump is all there. But there is one more thing that we have yet to account for, and that is the same issue that plagues many positive displacement pumps, and that is that their displacement is fixed. To understand why having a fixed displacement is an issue, we've got to bear in mind that the oil demand for the engine actually varies based off of a number of different factors. But again, since each one of the pistons only moves up and down so much based off of the geometry of our swash plate, we know that for every one revolution that the engine spins over, there is a fixed amount of oil that is going to be expelled from the high-pressure oil pump. Now, in an ideal world, the exact amount of oil that's produced by the high-pressure oil pump would be used and consumed exactly by the injectors, but unfortunately, that's not exactly the case. Additionally, all the high-pressure oil pump really does is move oil from point A to point B. In fact, in an ideal world, there wouldn't be any restriction and the high-pressure oil pump wouldn't actually produce any pressure at the output at all, but that wouldn't exactly be a high-pressure oil pump. So what's the deal? Much of the same mentality that we have with the high-pressure oil pump can also be applied to your most common garden hose. Now, we all know that if we take a garden hose and we put a restriction over the end of it, the water tends to shoot out at, well, what seems to be much higher pressure. Whenever you push your thumb over the end of a water hose, you know that the pressure increases. And effectively what you're doing is you're putting a restriction on the water hose. You have a pressure-producing device or a volume-producing device that was your house, and the pressure dropped inside of your water hose because there really wasn't a restriction. Now, whenever you put your thumb over the outlet, well, the pressure inside of the hose increases, which as a result causes your stream of water to shoot out at a very high velocity. And that's exactly what we need to do for our high-pressure oil pump. Instead of letting it just pump this oil without any back pressure, we need to effectively add in a restriction so that we can actually cause it to exert a force on the fluid, that is, the oil, so that it can produce serious pressure. Now, in the 7.3 Powerstroke's high-pressure oil system, the job of adding the restriction to the high-pressure oil pump is up to the IPR, or the injection pressure regulator, and it effectively does just what the name describes. It regulates injection pressure. Now, the injection pressure regulator works by way of a solenoid. Effectively, what happens is that the engine control module sends electricity through the IPR solenoid. This puts a back pressure on the oil inside the high-pressure oil system, causes it to be restricted, and as a result causes pressure to increase. Now, of course, you can't increase pressure too high, or you'll probably stall out your oil pump, or actually more than likely, you'd probably just break it more than anything. What you're effectively making the pistons inside the high-pressure oil pump do is actually exert and push a harder amount on the oil. If we take, for example, this little drawing here, you see that this piston on top has no restriction, and that the oil is able to just come out nice and easy like your normal water hose. But when you say put a restriction on it, or a very small hole is the outlet, much like you put your thumb over the end of your water hose, and as a result, the piston has to work a lot harder in order to push the oil out of the cylinder. Now, we could start getting off into the weeds and some really hardcore physics principles, but I think you get the point. The IPR adds a restriction that we can control so that we can regulate injection pressure. Now, the IPR actually sits in a port off to the side on your high-pressure oil pump, and effectively what it does is it blocks a bypass that would naturally let all the oil from the high-pressure oil pump out and back to the oil pan. But let's zoom in a little bit and take a better look at how the IPR works. Now, inside the IPR, there is a very small pin that effectively acts as a valve that creates a controlled leak, if you will. Effectively, what it does is, by closing the valve, you essentially seal up the high-pressure oil system. Whenever you let the valve open, you create a very small leak that lets high-pressure oil effectively leak out back to the oil pan. In the end, by controlling the amount of time that the IPR solenoid is energized or de-energized, we can effectively control how much pressure our high-pressure oil system actually has. And of course, the amount of time that the IPR solenoid is energized is controlled by the engine control module. Now, the relative amount of time that the IPR solenoid is energized is what's referred to as the duty cycle. Now, the duty cycle is typically referred to as a percentage. A 0% duty cycle indicates that the solenoid is off all the time. Meanwhile, a 100% duty cycle would indicate that the solenoid is closed all the time. And, of course, a 50% duty cycle indicates that the solenoid is energized only half the time. And again, the ECM will either supply power for a certain amount of time or not to effectively energize or de-energize the solenoid for the IPR. This effectively gives it the duty cycle. The duty cycle is, of course, controlled by programming parameters inside of your engine control module. Now, technically speaking, the IPR and the engine control module are sufficient to get the high-pressure oil system to operate and to get the engine to run. If you want, here's proof. So right now, the engine's running, and all it has is the IPR and the engine control module. But one thing you'll notice is that there is a check engine light. So that indicates there's something not right. And that's because there's one last sensor to the high-pressure oil system that we need to account for. Now, that last sensor that we need is what's called the ICP, or Injection Control Pressure Sensor. Now, it's located on the driver's side cylinder head in the oil gallery. The ICP sensor gives the engine control module a feedback for how much pressure is in the high-pressure oil system. And based off of that, the engine control module can adjust the injection pressure regulator's duty cycle. Now, having the ICP sensor for feedback allows the engine control module to have a much greater level of control over the high-pressure oil pressure. If you now take a look at this scan gauge 2 I have mounted to the OBD 2 port of my 97 F350, you can see we have a series of different parameters. Now, I've got engine oil temperature, and this value in the top left-hand corner is the IPR duty cycle. So you can see right now the IPR duty cycle is hovering around 10%. Top right is the exhaust back pressure, and right below that is the injection control pressure. That's actually measuring the oil pressure inside the high-pressure oil system expressed in PSI, or pounds per square inch. So right now we're hovering around 550 pounds per square inch in the high-pressure oil system. So the engine control module reads the amount of pressure in the high-pressure oil system and adjusts the IPR accordingly. So as you can see, as we hit the accelerator, the injection control pressure goes up and the engine control module adjusts the IPR duty cycle. Now, other factors affect this as well, such as tuning, for example. So over here, I go over to a hot tune, and you can see the ICP pressure went up, and so did the IPR duty cycle. Now, this is the hottest tune I've got, which actually defaults to increasing the ICP pressure to increase the amount of fuel that's delivered. So the engine control module reads how much pressure is in the high pressure oil system, and it corrects for what the actual pressure is with the IPR. So I've just disconnected the ICP sensor, and as you can see, it threw a check engine light because the engine knows that it's missing a signal that it needs. Now if you take a look at the scan gauge over here, we're still getting a high pressure oil reading, but that's kind of impossible if we don't have a sensor. So one thing you'll notice is that with the ICP sensor disconnected, the engine still senses some sort of pressure, and that's because it goes to a default value. Now this is another nifty trick that if you suspect you have a bad ICP sensor, you can disconnect it, and if your truck runs with it disconnected, then you probably know that your ICP sensor is screwed up in some way or another. Now bear in mind, these values you see on the ICP sensor are just assumptions that the engine control module is making. This is a standard that's good enough to get the engine running and to get you home. Now this converts it back to an open loop system, which is not quite as effective, and so really for optimal engine performance, you want to have that ICP sensor. Well folks, that does it for this video here today, and I hope you got a much better understanding as to how the high pressure oil system in your 7.3 Powerstroke works. Thanks for watching.